Welcome to the third module in the Environmental Geography course. This module is titled The Dynamic Geosphere and Plate Tectonics. I'm Nathan Bowden, your instructor for this course. In this module, you will learn the origins of plate tectonic theory, how scientists developed it and further tested it, the driving mechanism for geosphere movements and how plate tectonics work, how continents have split apart, moved, and reassembled, how Earth systems' interactions at plate boundaries are related to earthquakes, volcanoes, mountains, and ocean basins, as well as how tectonic processes affect people by creating both natural hazards and vital natural resources. Continental drift. What is continental drift? In the early evidence in the 16th century, they noticed that the continents seemed to link together. So Africa and South America seemed to fit like two puzzle pieces. Cold deposits and other strata, which are the layers of the geosphere on these separate continents, have similar fossils, such as the fossil here on the right-hand side, the Glossopteris, which is found in the southern continents, that is South America and Africa, and that they possibly formed one supercontinent at one time, which they named Gondwanaland. And the suggestion that the modern-day continents, now separated, were joined in Earth's past. So at this time we have 7 continents, and the suggestion is that many years ago, and we'll see soon how many years ago, all of these continents were together in one supercontinent. The original hypothesis of continental drift was proposed by Alfred Wegener. He was the first to formulate a detailed global explanation how these different continents and their present shapes fit together, and he laid the groundwork for theory on plate tectonics. Although at this time he did not come up with the idea of plate tectonics, he came up with the idea that continents drifted. So Wegener's evidence was he saw these different continents and they would fit together as puzzle pieces. You see this on the figure on the right-hand side, the different continents, Africa, South America, Antarctica, Australia, and India, that these fit neatly together into one continent. He noticed that widely separated but very similar sequences of sedimentary rocks containing the same fossils. Here we see the different types of fossils, the fossil of the land reptile, which matched across Africa and South America, the fossil of the Glossopteris, a fern, throughout the different continents, etc. He also noticed that glacial deposits appeared in Antarctica, and these were associated with ice flows which create land ridges radiating out from a central point. Lastly, ages of rocks were similar on mountain belts on different continents. So at a certain rock in the Indian continent or subcontinent matched with the corresponding mountain rocks in Africa. He called this supercontinent Pangaea. Pangaea is Greek for all land, and you see on the figure on the right, the very top, Pangaea. Collisions would have combined these continents together into one giant landmass approximately 250 million years ago, and then it slowly began to drift apart. Continents positioned on top of tectonic plates split and moved into present positions today. Notice that at approximately 150 million years ago, as shown in the figure on the right-hand side, you see the southern continent of Gondwanaland.
The breakup of Pangaea. The animation begins with a world map that shows Earth's current distribution of continents and plates of the lithosphere. Notice that most plates contain a whole continent or a portion of one, as well as a large region of seafloor. As a result, most plates include both continental and oceanic lithosphere. Also notice that most plate boundaries, shown by green lines, do not follow the edges of continents. Green arrows indicate the general direction of the plate movement. Plates are moving away from each other at mid-ocean ridge spreading centers, colliding at subduction zones or continental collision zones, and sliding past each other along transform faults. In the profile, you can see the subduction zone along the west coast of South America, the spreading center of the Mid-Atlantic Ridge, and the Indian Ocean floor to the east of Africa. About 200 million years ago, all of the present continents were assembled in the supercontinent known as Pangaea. At the same time, the oceans were combined into one huge ocean called Panthalassa, which included a smaller body of water called the Tethys Sea. Shortly after 200 million years ago, Pangaea began rifting apart, and the present-day continents began moving toward their current locations. By about 150 million years ago, Pangaea had broken into two smaller supercontinents, Laurasia in the north and Gondwanaland in the south. By 100 million years ago, the present-day Atlantic Ocean was beginning to open. India had broken away from Africa and was heading toward its eventual collision with Eurasia. By 50 million years ago, Australia had broken away from Antarctica. The collision of India with Eurasia created the Himalayan mountains and the Tibetan Plateau. This uplift began about 30 million years ago and continues today. The final portion of the animation projects the current rate and direction of plate motion into the future. You can see that 50 million years from now, the thin sliver of land that includes Baja California and coastal California will have separated from North America. The Atlantic Ocean will be wider. India will continue to collide with Eurasia and further uplift the Himalayas. And Australia will have moved northward to straddle the equator.
A few points about Alfred Wegener. His arguments for continental drift were in his lifetime seen as a failure because he did not have a viable mechanism for how the continents moved. He saw that the continents moved but had no clear idea supported for this movement. He did have a theory that the tidal forces generated by the Earth's spin would have pulled the continents apart, but basic physics say that this is, of course, impossible. And while his continental idea was a failure at the time and even ridiculed by the scientific community, his idea was considered later to be one of the most important in the idea of how the dynamic Earth worked. So, how do we go about explaining how the continents drifted apart? This theory is the theory of plate tectonics. One initial clue on plate tectonics was the moving of the North Pole. The North Pole, as shown in the figure on the right, has been wandering or moving around for hundreds of millions of years. And on the right-hand side, you see the path that the North Pole has taken in the last 500 million years. And explorations began as to understand how these the North Pole could have wandered so much. And ideas came about seafloor spreading. The bottom of the oceans were moving. They looked at the magnetic stripes. When sonar was developed, they could measure the magnetism of the ocean floor. And also earthquakes, theory on how they came about. supported this idea of plate tectonics. So the ocean floor was mapped, and as you see in this figure, so after World War II, they were mapped for partially because of the advent of large-scale production of submarines. They began to map the bottom of the ocean floor, and notice that these oceans had ridges, which are underwater mountains, and very deep trenches. A computer-generated map of the East Pacific Ridge, here on the right hand in the smaller part B of the figure, shows the difference in elevations on an East Pacific rise, the red being the highest elevation and the blue being the lowest. So how did these come about? We see now these ridges across the ocean floor. And so Harry Hess from Princeton University described in his book History of the Ocean Basins in 1962 the idea of continental drift, his explanation of continental drift. He recognized that this mechanism of continents being separated through the ocean crusts, either sinking and drifting apart at the trenches. He also noticed that the mid-ocean ridges, where a new oceanic crust forms, as the lithosphere, which is the upper part of the mantle, goes upward, and the mantle wells up, cools, solidifies, and separates. Volcanoes and a central rift valley are common among these fast-spreading ridges. A very good example of this is the Mid-Atlantic Ridge. So again, as I mentioned, the sonar was developed, and magnetic maps of the ocean floor could be made, and this happened in 1963 when Vine and Matthews, two geophysicists from Cambridge, went about mapping the Earth's magnetic field on the ocean floor. They were, as you see in the figure on the right, they went around in a boat with a sonar device. They dragged it slowly across the ocean floor and measured the magnetic fields. Additional data from magnetic mapping helped unravel the mystery of how these plates were moved. Because they noticed that the magnetic field stripes are arranged symmetrically about the center of the mid-ocean ridges.
Seafloor spreading and seafloor magnetization. The image shows a narrow ocean basin between two continental land masses. The oceanic lithosphere is created along a divergent plate boundary that coincides with a mid-ocean ridge in the center of the narrow ocean. The animation will illustrate the formation of additional oceanic lithosphere by seafloor spreading along the mid-ocean ridge, which causes the two continents to separate farther from one another. The animation also applies geologists' knowledge that Earth's magnetic field switches polarity at irregular time intervals of hundreds of thousands to millions of years. The current, or normal polarity, is one where a compass points toward the magnetic North Pole. During a time of reverse polarity, a compass would point toward the south. Since the polarity of Earth's magnetic field is locked into rocks when they first form, it is possible to study these changes of polarity by studying the magnetic fields of rock. New lithosphere, generated by igneous processes at the mid-ocean ridge, acquires a normal magnetic polarity, while Earth's magnetic field is in the normal orientation. When the field reverses, the new oceanic crust records the reverse magnetic polarity. Over time, Alternating bands of normal and reverse polarity crust form on either side of the mid-ocean ridge. The symmetrical pattern of these bands shows that the crust formed and spread away from the mid-ocean ridge, which causes the ocean basin to widen over time.
So how do they match it up? Well, firstly, they did analysis of the well-dated rocks on land. Here is an example of a 5 million-year-old basalt flow on Kauai, which is a Hawaiian island. That's shown in figure A below. So they measured every single layer along this 5 million layers, 5 million-year-old layer, and looked at the magnetic polarity reversals. So one layer would be positive, the next would be reversed, and then normal, and then reversed, and then normal and reversed. So they could tell when the reversal in the crust happened, and match that to the ridges that they were measuring at the bottom of the ocean. The timing and duration of these reversals were then correlated along the seafloor. So basically what they did was they looked at the layers in Kauai, correlated that magnetic reversal and normal along the layers, so using it as a ruler, and used this ruler along these mid-ocean ridges to figure out how old these ridges were. The age of the seafloor, here you see on the left-hand side a figure of the different ages of the seafloor, red being the youngest and blue being the oldest. And as you notice, there's a symmetry to the magnetic signature on the seafloor, which is also similar to this symmetry with respect to volcanic rocks on the seafloor. Again, red being the newest, where the new mantle is peeking through the crust of the lithosphere, and the colder colored regions, blue, are the older areas. Earthquakes are another test of plate tectonics, because as you see here on the left-hand side, the mid-Atlantic ridges, well, they produce land, and these two plates diverge from each other. It causes a friction along the default line. It doesn't happen it does not happen uniform along the ridge. Certain parts of the ridge will be slightly more active than other parts of the ridge and will grow at different rates. Earthquakes happen because these different growth rates along the mid-ocean ridge, and it develops a tension along the ridge. Eventually, in 1965, a seismologist named of Wilson had the idea of this lateral sliding. So this tension developed across the mid-ocean ridge, and at certain times, the tension breaks, and the ridges move quickly laterally along each other, creating transform faults. And this quick lateral transformation, this quick lateral movement, creates earthquakes.
Motion at a transform plate boundary. Transform plate boundaries are a special type of strike-slip fault that connect other segments of plate boundaries. They are called transform boundaries because motion is transformed from one boundary to another. In the animation drawing, a mid-ocean ridge is segmented by transform faults. Most transform plate boundaries are short and connect the spreading ridge segments along divergent plate boundaries. This animation shows how plate tectonics predicts transform faults should work where they connect mid-ocean ridge segments. Notice the motion of each plate away from the mid-ocean ridge segments that comprise the divergent plate boundary. New oceanic lithosphere forms at the mid-ocean ridges and moves away from the ridges. The transform boundary is the fault that separates adjacent seafloor that moves in opposite directions. Also, notice the inactive faults, also known as fracture zones, which appear to be continuations of the transform fault, but actually are not areas of plate motion. The plates on either side of a fracture zone move in the same direction and at the same speed. Examine the motion arrows along the transform fault. The motion of the seafloor demonstrates that the transform boundary is a left lateral strike-slip fault, even though the mid-ocean ridge segments seem displaced in a right lateral fashion. It is important to remember that the transform boundary transforms motion between the two divergent boundary segments and does not displace them. This is why the motion is actually left lateral and not right lateral.
In modern tectonics, we've identified many plates along the surface of the Earth, and these plates move very slowly, so only a few centimeters per year, which is approximately the speed at which your fingernails grow.
Plate boundaries. The plate tectonics model helps explain the development of many topographic features and regions of volcanic and tectonic activity around the world. Lithospheric plates interact with other plates along plate boundaries, of which there are three main types. Plates move apart at divergent plate boundaries, which are associated with features such as the global mid-ocean ridge and continental rift valleys. Plates come together at convergent plate boundaries, which are associated with features such as oceanic trenches and subduction zones or continental collision zones. Plates slide laterally past each other at transform plate boundaries, which are associated with transform faults that occur along the offset segments of the mid-ocean ridge. Divergent plate boundaries and seafloor spreading. New ocean floor is created at divergent plate boundaries such as the mid-ocean ridge through a process called seafloor spreading. The mid-Atlantic ridge is an example of a divergent plate boundary. Notice that as the edges of the two oceanic plates spread apart at the ridge, magma from the upper mantle rises and solidifies in the gap to form new ocean floor. Over millions of years, the ocean floor moves away from the mid-ocean ridge in opposite directions. As a result of seafloor spreading, the youngest ocean floor is found along the crest of the mid-ocean ridge. At greater distances in either direction from the crest of the mid-ocean ridge, progressively older ocean floor is found. This pattern exists throughout the world's oceans. Convergent plate boundaries and subduction. As the animation progresses, notice that at the margin of the continent, oceanic lithosphere descends back into the asthenosphere in a process called subduction. Oceanic lithosphere subducts because it is denser than continental lithosphere. As the oceanic lithosphere descends, it produces a deep oceanic trench along the edge of the continent. The Peru-Chile Trench along the west coast of South America is an example of this kind of feature. Notice the magma rising from above the subducting oceanic plate. As the subducting plate is heated at depth, some of it melts. Once molten, this low-density material rises toward the surface above the subduction zone. At the surface, highly explosive volcanoes occur, creating an arc-shaped row of active volcanoes called a volcanic arc. The Andes Mountains of South America and the Cascade Mountains of North America are examples of continental arcs, which are a type of volcanic arc that occurs on land. In addition to the oceanic plate to continental plate subduction zone, illustrated in this animation, oceanic plate to oceanic plate subduction zones also occur. These produce island arcs, which are a second type of volcanic arc that consist of a row of oceanic islands. The Aleutian Islands and the Mariana Islands are examples of island arcs that develop from oceanic plate to oceanic plate subduction. Transform faults and boundaries. In locations where the edges of two plates slide laterally past each other, a transform fault is formed. Notice the short transform fault in the offset along the mid-ocean ridge. Here the edges of two plates are sliding past each other in opposite directions. A prominent example of a major transform boundary within a continent is the San Andreas Fault of California.
An example of a divergent ridge, two divergent plates creating a rift, is shown here in Africa. The upswelling of the asthenosphere is as part of the mantle peeking through the lithosphere will thin the lithosphere. It will basically heat it up through pressure, but also just through heat. It will thin and separate. And this you see on the right-hand side on the map, the divergence of the Arabian and African plates along the Red Sea, but also again between the two African plates along the East African Rift Valley. And these two African plates are the Somalian and the Nubian plate. So basically, Africa is splitting apart in the same way that Pangaea split apart, as stated by Wegener, and this splitting did happen about 250 million years ago. Continental splits. How does that happen? Well, as I quickly mentioned, but now I will go into more detail. The rifting starts when the hot asthenosphere part of the mantle begins to rise. The upwelling in the asthenosphere heats and weakens the crust, resulting in a thinning of the lithosphere, and also it's called normal faulting, the creating of a rift valley. Crustal extensions proceeds as the asthenosphere continues to peak upwards. It eventually splits apart, and the continents migrate away from each other as the mantle upwelling continues, and oceanic crust forms where the continents once joined. Divergent plate boundaries can also, these can happen on the seafloor as well as on land. In Africa, it's in the eastern Rift Valley of Africa, it's happening on land. But of course, it can also happen, as you see here on the left-hand side, underwater. And these form very mineral-rich hot spring waters and hydrothermal vents, which are also called black smokers, because of the rich amount of nutrients coming upward. As you remember, the mantle has significantly higher concentrations of certain elements such as iron and nickel, and these give it these black smokers their black color.
Forming a divergent boundary. Although most modern divergent plate boundaries coincide with mid-ocean ridges, these boundaries have usually originated within continents. Tensional stress extends the continental lithosphere by brittle faulting in the upper crust and plastic flow in the lower crust and lithospheric mantle. Normal faults form a rift valley within the continent. Rising lithosphere and asthenosphere mantle decompresses to form magma that erupts as volcanoes. Eventually, the tensional stress separates the continental plate into two pieces. Upwelling asthenosphere melts to form mafic magma that solidifies to form new oceanic crust. The unmelted residue of the asthenosphere remains as new lithosphere beneath the oceanic crust. Sediment accumulates in the early rift valleys and along the new continental margins as the continents drift apart, while new oceanic lithosphere forms between them.
Not all continents are divergent. They are not all continents are drifting from each other, far from it. Many plates are convergent, which means they are approaching each other. Here we have a figure of on the left you see a divergent plate boundary. That is saying that the rising asthenosphere is causing plate B in this picture to move away from plate A. So A and B are diverting. However, as plate B diverts from A, it approaches plate C. And this is a convergent plate boundary. Convergent plate boundaries are when these two plates move toward each other. And they can be between two oceanic plates, an oceanic plate and a continental plate, as shown here in figure 318 at the bottom, or between two continental plates. The Himalayas is an example of two continental plates which are converting, or convergence, and which they form the Himalayas, of the largest, tallest mountains on the planet. So where these continents converge, neither of them is dense enough to sink into the mantle, so they form a suture zone. When they meet together, and these plates, the Indian and Eurasian plates, they form, and it's through this great suture zone collision, the world's highest mountains. Thrust faults are beyond the mountains, where the crustal shortening areas converge on their boundary. So the land boundary of the two plates is the thrust fault. The mountains happen where the one plate subducts under the other plate under great pressure.
The collision of India with Eurasia. The map you see shows the present-day Indian Ocean basin. The Himalayan mountains and the Tibetan Plateau are to the north of India. These mountains began to develop about 30 million years ago, when the subcontinent of India commenced its collision with the rest of the Eurasian continent. About 250 million years ago, all of the present continents were assembled in the supercontinent known as Pangaea. By about 200 million years ago, Pangaea was rifting apart and the present-day continents were moving toward their current locations. The map you see now shows the position of India 71 million years ago. India has broken away from Pangaea and is moving toward the Eurasian continent. By about 30 million years ago, India started its collision with Eurasia. When the edges of the two continental plates collide, the material is too buoyant to subduct. Instead, mountain ranges are uplifted through folding and faulting. The collision of India with Eurasia uplifted the Himalayas and the Tibetan Plateau. This collision continues today. You now see a profile view of the Indian landmass before it began to collide with Eurasia. Notice that the subduction of ocean floor is taking place beneath the region now known as Tibet. As India moved toward Eurasia, more and more of the intervening ocean floor was subducted. You now see a profile view of present-day India and Tibet. The Himalayas were uplifted as part of a continental suture.
Two oceanic plates that are meeting and converting. An example of this is the Aleutian Trench in Alaska. As you see in figure A on the left, at the top, these two plates meeting together, the one being the North American plate to the north and the Pacific plate to the south. Along this plate there are many earthquakes, and also a few volcanoes which create islands. And most of these earthquakes happen underground, very deep under the surface, the ocean floor. Strike-slip faults happen when two plates are neither diverging or converging. Rather, they are running past each other, parallel to each other. And the most common of these faults is a strike-slip fault. Here we have a picture on the very right-hand side, a famous strike-slip fault, the San Andreas Fault in the west coast of North America. It's called the San Andreas Fault. And you see a picture of a farm where the fence has been slightly repaired due to an instance where these two lands on top of the two plates are moving parallel to each other, one heading northward, the other one heading southward. This certainly came in one big movement called a earthquake. And at this time, the Earth moved approximately, I see, about 2 meters. So as I mentioned, the San Andreas Fault is one of these slip plates. And this movement, the photo here showing it, is the Great San Francisco Earthquake of 1906. We can also see these slip plates along the San Andreas Fault on the left figure, a photo of rivers that have drastically been moved because of these plates moving against each other. And also these can be filled up with water, and lakes, linear lakes, can form.
Motion on faults. Faults are fractures along which rocks move. Geologists describe the rocks below the fault as the footwall, in contrast to the hanging wall rocks present above the fault. A normal fault forms when the hanging wall rock moves downward compared to the footwall. Normal faults form where tensional stresses stretch the crust. Notice that the rocks exposed at the surface of the eroded and uplifted footwall block are older than those exposed on the hanging wall side of the fault. A reverse fault forms when the hanging wall block moves up compared to the footwall, and where the fault dips at an angle steeper than 45 degrees. A similar fault inclined at an angle of less than 45 degrees from the surface is a thrust fault. Reverse faults form where compressional stresses shorten the crust. Notice that rocks exposed at the surface of the eroded and uplifted hanging wall block are older than those exposed on the footwall side of the fault. Strike-slip faults form by movement along the strike direction of the fault plane. The blocks of rock slide horizontally past one another instead of up and down along the dip of the fault plane. Strike-slip faults form where shear stresses deform rock without any stretching or shortening across the fault. Notice the stream channel displaced by the fault motion. Notice that, regardless of which side of the fault you look from, the stream seems displaced toward the right. This sense of fault motion describes a right lateral strike-slip fault. If the fault blocks had moved in the opposite direction from that indicated by the arrows, then this would be a left lateral strike-slip fault.
As I mentioned, plate tectonics and earthquakes are very deeply related. The distribution of earthquakes is a good guide to showing where these plate tectonic boundaries are. On the left-hand side, you see the distribution of earthquakes along the Earth, and most of these earthquakes occur along the convergent and transform plate boundaries, and the most devastating of these being in the Pacific Ocean rim. Offshore earthquakes can often displace ocean waters, and these generate seismic sea waves, also called tsunamis. A very tragic incident that happened in 2004, a very tragic tsunami in Indonesia that killed approximately 250,000 people. Tsunami is Japanese for harbor wave, as one student of mine mentioned to me. Plate tectonics and volcanoes, as I mentioned, here on the left you see a picture of Mount Pinatubo, which is a volcano in the Pacific rim, and where these earthquakes happen, where these plates are, volcanoes are often surely to come about. Plate tectonics, such as the Himalayas, also build mountains. Here's a photo of the Chugach Mountains. This mountain building can happen in several forms. The first is accretion. The Chugach Mountains in Alaska are an example of accretion, which is the off-scraping of seafloor sediments against an overriding plate of convergent margin, producing mountains. Compression at convergent plate boundaries, just through the sheer physical compression, mountains can form. The collision of continents as one continent goes above another continent is a third way in which mountains are formed. And lastly, the magnetic processes help form large mountains. And these large mountain ranges can be shown on the oceanic plates converging and subducting beneath the continental margin. These plates have negative consequences, as I mentioned. Tsunamis, earthquakes, volcanoes can be quite disruptive, but they also have positive impacts on our other Earth systems. On the left-hand side, the Andes Mountains were formed by this continental movement. The Andes Mountains stop the flow of warmer air, which condenses along the mountain ridge and falls as rain. This rain can be used to great effect for agriculture. And on the right-hand side, we see the Bingham Canyon copper mine in Utah, which happened because of a subduction-related volcano. Again, as I mentioned, these volcanoes bring very rich minerals to the surface from the mantle, and some of these minerals include such metals as copper. In summary, what have we learned? First, that persistent research, the applications of new technology, and the synthesis of diverse observations over more than 3 generations of scientists have concluded in our 20th century and now 21st century developed theories of plate tectonics. Earth's rigid lithosphere is broken into pieces called tectonic plates, so this hard, rigid lithosphere of the crust is floating on a softer mantle, and these pieces are called tectonic plates. These plates move apart. We have divergent boundaries which create new seafloor or rifting on land. These plates can come together, forming convergent boundaries. Convergent boundaries also often involve volcanic mountains or major earthquakes. Alternatively, these plates can slide horizontally past each other, forming transform faults, slip faults, which again also create earthquakes. And lastly, plates localize volcanic and seismic activity, and plate motion influences the biosphere, as shown by the Andes Mountains green growth, the climate, as the atmosphere moves across the mountains, the vapor condenses and rains, and of course the availability of natural resources such as copper. Thank you for listening to this third module. If you are finished, you may continue to the next module.